In the previous video tutorial, we introduced the first law of thermodynamics and we saw how it could be applied to closed thermodynamic systems. In this video tutorial, we're going to extend that theory and see how it can be applied to open thermodynamic systems. So first of all, we'll discuss what we mean by an open thermodynamic system, and then we're going to recap the first law of thermodynamics before seeing how it can be applied to our open systems. Finally, we'll see how we can derive something called the steady flow energy equation, or shortened to SFEE, and then we'll see how it can be applied to open thermodynamic systems. So just to recap, a thermodynamic system is a region of space that has a specific boundary that separates it from its surroundings. Depending on what is contained within the region of space and what can cross the boundary determines the type of thermodynamic system. So when we consider open thermodynamic systems, both energy and mass can transfer into the system or into the region of our thermodynamic system. Recall that for closed systems, only energy could transfer and mass could neither flow into nor out of the system. And that's the fundamental difference between the two types of system. So as an example, we might have a radiator in a domestic premises. As we can see, water flows into the radiator, water flows out of the radiator, therefore we must have an open system. We're also going to have energy transferring from the system, assuming that the radiator is hot, because heat is going to be lost from the working fluid and transferred outside of the system to the surrounding air. So we can see the fundamental difference there when compared to our closed systems. A more typical example might be some kind of turbine that's used to expand steam. And once again, we see that mass flows into the system, and we also see that mass flows out of the system. The key difference between our radiator is that the radiator is transferring heat to the surroundings, and our turbine here is transferring work or power to the surroundings, or outside of the thermodynamic system. So now let's see how the first law of thermodynamics can be applied to open systems. Once again, the first law of thermodynamics comes from the law of conservation of energy. Energy can neither be created nor destroyed. Energy can only be converted or transferred from one form to another. And for our open systems, we're going to look at the rate of transfer of all energy types out of the system, and we're going to set that equal to the rate of transfer of all energy types into the system. So what different types of energy do we need to consider? First of all, we need to consider kinetic energy. We can see from our diagram that the fluid flowing into the system has a velocity, and we can see that the fluid flowing out of the system has a velocity. So we don't know for certain that the kinetic energy of the fluid exiting the system is the same as the kinetic energy of the fluid entering the system. The other thing we need to consider is potential energy. We can see that the inlet to the turbine is at an elevation above the outlet to the turbine. So at the inlet we have more potential energy than we have at the outlet. We also have heat energy. We might have heat being lost from the turbine, or we might have heat being applied to the turbine. Another form of energy to consider is work. The purpose of the turbine is to expand steam in order to generate mechanical power. So we need to consider how much energy is being produced by our turbine. Now, the final type of energy that we need to consider is something called enthalpy. And enthalpy relates to how much energy is stored in the fluid. In actual fact, it's the amount of energy that can be recovered from the fluid. So the amount of energy that can be recovered from the fluid entering the turbine is presumably going to be higher than the amount of energy that can be recovered from the fluid exiting the turbine, because what we're doing is we're removing usable energy from the fluid in order to create mechanical power. So let's be a little bit more specific when we see how this applies to the steady flow energy equation. Now, because we have a mass flow rate entering the system and we have a mass flow rate exiting the system, what we're actually going to consider is the rate of change of different types of energy. So we're going to consider the rate at which kinetic energy enters the system, and we're going to consider the rate at which kinetic energy exits the system. We're also going to consider the rate at which potential energy enters the system, and we're going to consider the rate at which potential energy leaves the system. Now recall that potential energy is mass times gravity times height, but as we have mass flowing into the system, the amount of potential energy within the system is going to change. And as we have mass flowing out of the system, the potential energy leaving the system is also going to change. So we need to consider the rate of change of potential energy. We're going to consider the rate of heat going into the system or out of the system, and we're going to consider the rate of work going into the system or out of the system. In this example here, we have heat leaving the system or heat out, and we have work being produced by the system or work out. So our rate of heat loss would be negative as heat energy leaves the system, and our rate of work done would also be negative because we're drawing mechanical power out of the system. Finally, we're going to look at the rate of enthalpy in and out of the system. So the rate at which enthalpy changes or enters the system, and the rate at which enthalpy exits or leaves the system. So let's start from first principles. We know that the amount of energy exiting the system must be set equal to the amount of energy entering the system. Now I've used subscript 2 for exiting the system, and I've used subscript 1 for entering the system. So let's consider each of these types of energy. We have the rate of kinetic energy exiting the system. We have the rate of potential energy exiting the system. Recall that it's the rate of potential energy leaving the system because mass is flowing out of the system. And we have the rate that enthalpy is exiting the system. Those terms are repeated on the right-hand side because we have the rate of kinetic energy entering the system, we have the rate of potential energy entering the system, and we have the rate of enthalpy entering the system. Now, sticking with our convention then, we also have heat going into the system, and we have power going into the system. This symbol here, phi, represents rate of heat transfer into the system, and P is mechanical power or rate of work being done on the system. So we could have replaced this with Q over S for heat energy per second and W over S for work done per second. But the symbols phi and P are more typically used. Now we're going to rearrange this slightly, and all we're going to do is we're going to collect kinetic energy, potential energy and enthalpies on the left-hand side. We have the rate of kinetic energy exiting the system minus the rate of kinetic energy entering the system. We have the rate of potential energy exiting the system minus the rate of potential energy entering the system. And we have the rate of enthalpy exiting the system minus the rate of enthalpy entering the system. And on the right-hand side, we still have the rate that heat's entering the system and the rate that work's being done on the system. Now we can actually simplify this further. You can see I've moved the right-hand side to the left-hand side. So we have the rate of heat energy into the system plus the rate that work's being done on the system, or the power entering the system, equals the change in kinetic energy per second plus the change in potential energy per second plus the change in enthalpy per second. And on the bottom line there, that's actually our steady flow energy equation, SFEE. Another important takeaway from this video is, depending on the scenario or depending on the system, we can actually begin to cancel some of these terms out. So I recommend always starting with the full steady flow energy equation and then analyse the system in order to see which terms are no longer relevant in the formula. And I'll give you an example of how to do this. If we return to our example of our domestic radiator, we had water entering the system and we had water exiting the system. We know from continuity that the mass flow rate of water entering the system must equal the mass flow rate of water exiting the system. Now, as that's true, and as the inlet and exit are at the same height, the rate of potential energy entering the system must equal the rate of potential energy leaving the system. Therefore, we know that there's going to be no change in the rate of potential energy per second. What that would mean is we could completely disregard this term here. We would just cross that out and not include it in the formula. We also know that if both the inlet and outlet have the same diameter bore, typically in a central heating system, this might be 15 millimeters, then the velocity of fluid entering the system and travelling around the radiator must equal the velocity of the fluid exiting the system. Therefore, if the velocity at inlet equals the velocity at outlet, and the mass flow rate at inlet equals the mass flow rate at outlet, then we also have no change in the rate of kinetic energy into or out of the system, and once again we can disregard that term. We can also see from inspection that no work's being done on the fluid. We're not compressing the fluid or allowing the fluid to expand. Therefore, no mechanical work or no power is being inputted to the system. What we do have though is we have heat being lost from the system. So the rate of heat transfer out of the system would actually be negative here on the left hand side. And we're also going to have a change of enthalpy of the fluid. So as the water gives up heat energy, we would actually see a change in its enthalpy. And we'll see how enthalpies can be determined in a later tutorial. But for now, the important thing to remember is the best thing to do is always start with the full steady flow energy equation and then analyse the system in order to see which of these terms can be removed. So just to summarise, in this video we've seen how the first law of thermodynamics can be applied to open systems. We've seen how we can derive something called the steady flow energy equation by beginning with our first law of thermodynamics. And finally, we've discussed how we can take the steady flow energy equation in its complete form and begin to remove terms that aren't relevant to a specific thermodynamic system.